Alright guys, so hopefully you watched my first video, which is just a 5-minute sort of demonstration, animated demonstration of waves in a virtual ripple tank. Okay, and normally, because the pandemic has completely changed the way I would normally teach this, I would normally give you this little sheet where you fill in these little dots and circles here, and then we try to understand this interference pattern together, like just in class together. So I'm just going to have to do my best to explain it to you here. All right, so before we start talking about this pattern, I'm just going to say note at the top here. Okay. Okay, so yeah. Oh yeah, I guess I will write it down. I was going to change my mind here for a second, but I'm going to write it like this. Okay, I'm just going to say crest plus crest, or trough plus trough equals constructive interference, right? Okay, and then also crest plus trough. I'm just going to say these 2 points, crest plus trough, though, when there's opposite, you get destructive interference. And that means like they sort of cancel each other out. Now, if they're equally sized, okay, interference. Now I'm running out of room there. Okay, but that's basically it. Okay, now, also, just a little note on waves. Here you can sort of see the, no, actually I don't have room there, so forget it, I'll just leave it. I was gonna say that, like, maybe I'll do it down here. If you have a sinusoidal wave, okay, crests and troughs like this, we know that a wavelength, okay, is the distance between two crests, or the distance between two troughs. And like, if I want to know what the distance is between a crest, like at the top of a crest and the bottom of a trough, well, that would be half of a wavelength, right? From there to there, okay, would be half of a wavelength. So just a couple of notes there, okay, that are relevant for this. All right, so here's the deal. Here we have two sources, okay, so about this picture, S1 and S2 are two sources, okay, of circular waves vibrating in phase, which means basically they're bobbing up and down in the water at the same exact time, okay, each producing a crest at the same moment in time, okay, and at the same frequency. Okay, so they're both producing waves that are the same wavelength, the same period, the same frequency, right? Even the same size, okay? And they're vibrating in phase. So these are two identical sources, right? So the waves they make are identical, and they're making them at the same time, and that's really important, okay? And so that's what this picture represents. Now, where the waves meet are indicated here with dots, okay? Like filled in dots and hollow dots. So let's zoom in on this. Okay, and what I'm going to do is I'm going to highlight using my sort of rainbow colors here points I'd like you to consider for a moment. Okay, so here's the deal. What we're going to do is we're going to focus on this part of the pattern right down the middle. Okay, so I'm going to color this dot in over here. Okay, and I'm going to call it PM. Okay, it's a point in the water. That's why it's called P. Now, if I were to draw a line, and I'll use yellow highlighter here for a second, I'm going to erase this anyway, but I'm going to draw a line from there to there, just freehand. Normally I should use a ruler, but I can't do that. I'm just sitting on my bed here doing this because my office space is being used today. So, all right, so look. A wave that is generated from the first source, S1, will travel along that line, okay, and then it's going to pass through that point, PM. Now, a wave traveling from S2 will travel along the other line on the other side, and it'll get to that same point. Now, what we notice is all the way down the middle, you're always getting crest and crest, or trough and trough. So let me zoom in a little more. The dotted lines here, these dotted lines, oh, sorry, let me get rid of that. I'll use a blue color. These dotted lines here represent troughs. So that is a trough that came from S2. This is a trough that came from S1. And they meet right here on this point. Okay, they meet right there, producing constructive interference. Now, these lines here, which I'll color red, these lines are crests. Okay, this one came from S2. It'll let me write the letter S, S2, and this one came from S1, but they meet right there, okay, and you get constructive interference. Now, if you look down the line here, you constantly get constructive interference. So here's another spot where two crests are meeting right there to get constructive interference. Here is a spot where two troughs are meeting right here to produce constructive interference again. See, crest and crest, or trough and trough, you always get constructive interference. Now a line forms down the middle, okay? If I shade that in using a rainbow color, a line forms down the middle, and all the way down that line is an area of constructive interference, okay? We call this area the central maxima. Maxima means constructive interference, okay? For light, it means it's going to be a bright spot, okay? But for waves, it just means an area of constructive interference. We call it a maximal point or maximal line in this case, okay? So right down the middle, you get constructive interference. Now, I try to explain this to students. Why do you get constructive interference all the way down this middle line, okay? Well, the reason is waves traveling from, because it's right in the center, okay, this line, the two waves travel the same distance from both sources to get there, okay? That means those two yellow lines are always going to be the same length, right? Now, if I were to erase these two yellow lines, I said I would erase them. If I were to erase these lines, okay, and draw yellow lines going from anywhere you like. Let's say I want to pick a different point. Let's say we go here, okay? Whoops, that's terrible. And then the other one was here like this, okay? So a wave to get to this point here, okay, to get to this point, and I'm going to just color in here like this, to get to that point, waves have to travel the same distance from source 1 and source 2, okay? So in other words, the path that the waves are taking from both sources are the same length on either side, okay, of that center line. And so that's why you get constructive interference, is because each source is generating a crest at the same time, and then the crests take the same amount of time to arrive at the center, no matter where you are on the center line. And so they're always going to be meeting at the center, crest, crest, trough, trough from those two sources, because they're making crests and troughs at the same time. So they're going to meet at the same time in the center, okay, because they take the same amount of time to arrive there from both of those sources, okay? And that's why you get that line of constructive interference down the middle. Now, if you want to know what that looks like in the three-dimensional picture, I copied it over here, okay? That line, okay, down the center, this is a little bit off axis here. Okay, so I've got 1, 2, 3, 4 nodal lines. Okay, so that line, I'll use my rainbow color, is right here. So this region in here is an area, okay, and I'll just sort of shade it in, of constructive interference, okay, all the way down there. The two sources are right, this is, remember, on an angle, it's three-dimensional. The two sources are like S1 and S2 over there, and we're only looking at, in our little cutout here, the top half of the picture. The bottom half, there's interference too. In other words, we can see the corresponding bright line down the center right about there, area of constructive interference. Okay, so if you look at this picture, we're only seeing half of the picture here. That line down the center of constructive interference is right here. I'll color it in even more. You get constructive interference all the way down this line because the waves take the same amount of time. They travel the same distance from each source to get to any point on that line. So you always get constructive interference there, always crest meeting crest or trough meeting trough. Okay? All right, so that's how you explain that middle line. Now right next to it though, and I'm going to use the color blue, or no, I'll use blue. Okay, so here's the deal. In the next line here, these hollow circles, I'll shade in a line, these represent an area of destructive interference. Now, how do I know it's destructive interference? Well, here, if I zoom in on that top point, okay, here my crest, okay, that is centered at source 1, meets this point, but that's where the trough from S2, this trough comes from source number 2, and when the red line meets a blue line right there, we get an area of this, you put a circle around it, the hollow circle means an area of destructive interference. Crest meeting trough, right? Solid line meeting dotted line. Or here my red line meeting a blue line. Okay? Now if we go down to the next point, here's a crest, this time coming from, that's a crest. This one came from source 2, okay? Because that's where the center of its circle is, that circular arc. But there's a trough right here that came from this dotted line here, okay? That came from source 1, but again, right there, in the point of intersection right there, we again get an area of destructive interference, right? Now, when you go all the way down this line, what we're going to find is you always get destructive interference. Look, always. Every circle is an area where a crest is meeting a trough. It's always destructive interference. Okay, so how come, right? Like, what's the deal? Okay, now I'm going to show you that over here. So I'll stick to my color blue. Okay, so we're seeing right here, this region, it forms a very distinctive valley in between my waves, okay, or my lines of constructive interference. And there's another line on the other side of the pattern right here, same thing, okay? So what I'm going to do is go over here. I'm going to zoom in on this picture again. We call a point on this line, I'll use black. We're going to call that PN, okay? Now, we use N for destructive interference, M for maxima, and N is for nodes, okay? So M is for maxima, okay, which stands for like constructive interference. N is for nodes, which stands for destructive interference. Now, if you look, there's another line of destructive interference, and I'm going to color this one blue also, right here. Now that line has something in common. These two blue lines that I've drawn in the picture, I'm scribbling in, these two lines have something in common. They're both on either side of that center antinode, okay, where you get constructive interference. So this is PN here. Also, this point here, we call it PN. Okay, so if you look at the pattern, in the middle we have constructive interference, and then on the right or left of the middle, we see a line of destructive interference. But then after that, we see a line of constructive interference. Okay, so here, going down this line, I'll use my rainbow color again. Here is a line of constructive interference, right? Okay, and I'll just continue this down here like this. And then right after that, and I'm going to color this in on the other side also, there is another line of constructive interference, right? Okay, and you can see they've marked off the lines for us with dotted lines. It's a bit confusing, but yeah, I mean, this picture is confusing, I have to admit. That's why I'm taking such pains to explain it to you, okay? Because it's important that you get this. This unit is not a difficult unit. Some of the stuff is a bit unusual, but like we've never really done problems like this before. But it's just a matter of using the equations. But in order to understand what the equations mean, okay, I need to go through this diagram and explain it in detail. I'll go back to my rainbows, color this in a little bit better. All right. Now what I'm going to do is I'm going to color in all the lines. Okay. All the constructive interference lines, I'm going to use a rainbow color. Okay, so here's my next one. I'll just color all the constructive lines of constructive interference. Okay, like that and like that. Those are all the lines of constructive interference that you see. And then I'll use blue to color in. I know it's so much fun. This must be so much fun for you to watch me coloring this in. All right. So there you go. There are all my lines colored in. Okay. Now, what you're seeing is alternating lines, constructive and then destructive interference, and then constructive interference and then destructive. So as we go around the circle, you know, here, I'm going to highlight the areas of destructive interference. So here we see one. Then in between those two yellow lines is a line of constructive interference. And then, you know, so here's one line of destructive, then a line of constructive, then a line of destructive. And then a line of constructive, then another line of destructive here, then a line of constructive again, then another line of destructive here. And then on the other side of the pattern, same thing. Destructive, then constructive, then destructive, then constructive, then destructive, then constructive, and then destructive again, right? So that's basically it, okay? Now, what I'm going to try to do is explain to you, and I'm going to explain the equations that come with this, explain to you like exactly why this pattern is happening. Now, by the way, on this picture here, this is a line of constructive interference here. And then right after it, a line of destructive interference, a little valley, right? And then right after it, a line of constructive interference like this. And then right after that, a line of destructive interference, and then one last line of constructive interference, which is right there. Okay, they're quite wide, right? And then the last line of destructive interference is right there in that valley right there. On this side, we'll color these in too. Oh, that's really bad, but anyway, whatever, it's not a big deal. Okay, there's a line of constructive interference. There's another line of constructive interference right there. And our last one right here, and then in between those, here you can see these valleys really like these dead spots. They're called nodal lines because they're not really nodal points. They form lines, so we call them nodal lines, right? So here we see alternating, rainbow is bright, blue is dark, okay? Constructive, then destructive, constructive, destructive, constructive, destructive interference, right? As the pattern radiates outwards, okay? Sort of working your way around the circle. All right, so let's get back to this, okay? And I'm going to explain to you how this works. So there's something called path difference. So I'm going to start using black here. The path difference okay, is the difference in distance from a point in the pattern, okay, to the sources Okay, now let me explain what that means mathematically. Okay, so let's talk about the antinodes for a second, or the antinodal lines. And then I'm going to say these are aka maximum, or maxima for plural, okay? Or in light, we call them bright fringes, okay? The path difference on the antinodes, okay, we use PD for path difference, okay, and that would equal PM S1 minus PM S2. And normally we put absolute value signs around this depending on which side of the center you're measuring from, okay? Now we use the letter M, and let me explain what the letter M means. M is a number starting at 0, and you just continue like this, and it represents the antinode line number. Okay, so let me show you this picture here. Okay, so in this picture here, we have 8 blue lines, and 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7 rainbow lines. Okay, now there's one rainbow line that is dead center. So I'm going to use my rainbow color, that one there. Okay, that's dead center. That's M equals 0. Okay, so there is no difference in path anywhere along that line from waves coming from S1 and waves coming from S2. They both travel the same distance to get on that line. Now this one here, this next bright line, that one is M equals 1. Okay, and on the other side here, that's equal to 1 also. Okay, so we just number them. This one is 2, and that one is 3. And on the other side, there's symmetry down the middle of the picture, right? So this is M equals 2 and M equals 3 also. Okay, so we count from the center. The center, we start at 0, and we count left or right, okay, or clockwise or counterclockwise, starting at the center. So here, if you want to do it from here, this one is M equals 0. This is M equals 1. M equals 2. And over here is M equals 3. Okay? Then on the other side of the picture, they're the same number system. So this is M equals 1, this line, right? The next line of constructive interference, M equals 2, and then finally, M equals 3. Okay? All right. Now, the pattern, this picture is going to get really messy, but I'm going to erase my two, try not to erase too much. I'm going to erase my two things there. I'm going to color this blue again. So I accidentally erased it. Okay, so there you go. Now, here's the deal. What do I mean by path difference? Well, okay, pick a, look, the center one's kind of obvious. So here, let's go down the center. That's the easiest one. So if I draw a line from here to here, and from there to there, okay, this line here would be P1, or sorry, P0, like the M is 0, right? S1. And my point would be P0. P0 in here. Okay, if you see it, where the point where they meet is P0. And then this line here is P0, S2. Now those two lines, those two yellow lines that you see have to be exactly the same length. Okay? And when you subtract their lengths then, what are you going to get? Well, 0. So the path difference is 0. In other words, there is no difference. They have the same length. okay? So that's going to be true no matter where I am on the center line, right? So if I just erase this one and erase that one, and I pick some other point down the middle, okay, let me go back to my highlighter. Let's say I pick some point up here, right, whatever. Well, those two lines are going to be the same length also, right? Even though I've drawn them terribly, so they're probably not the same really, but okay, let me erase those two. Now if I pick some point at the very top, okay, all the way up there, those two lines are the same length. As long as I'm down the center of the picture on that center area, you're going to get the same length of the two lines. So the path difference is going to be 0. Okay. So let me erase this because I've changed everything. So if that makes sense to you, and I'll erase this little guy too, if I can. All right, and let me color in my rainbow again down the middle. All right, so there's my rainbow. Okay, so I hope you understand this little expression here. It's what's saying is the difference in length of two lines. These are line segments, PMS1, PMS2. Now watch. What about at m equals 1? So what if I pick a point on this node at m equals 1, and I go up there like this, and up there like that? Well, now, clearly, this one, P1S1, it's on the first node. I'm having a hard time. P1S1, like that. And this guy, P1. Now they're not the same length, okay? Clearly, the one that's on the left side is longer than the one on the right, okay? But how much longer is it? Well, we actually know. You could just measure, okay? We know how much longer it is, okay? We have a formula that, here, let me explain. What you do is, for the antinodes, so for these antinodal lines, what you'll find is that the path difference is equal to m times the wavelength, where m is equal to 1, 0, 1, 2, 3, and so on. Okay? So what's happening is, if the difference in path of the two waves is a whole multiple of a wavelength, you're going to get lines of constructive interference. So that includes 0. So if there's no difference, that's right along the middle. So here, the path difference here is 0. So here the path difference equals 0. Okay, anywhere along that line. But here, anywhere along this line, the path difference is actually a full wavelength. Okay, anywhere along this line, the path difference is equal to 2 full wavelengths. Okay, and anywhere along this line, the path difference would equal 3 full wavelengths. Okay, so what's happening is you're getting, whenever the path difference is a whole multiple of a wavelength, you're still going to get crossing over each other, crests and crests and troughs, constructive interference, right? That's what you're going to get. So you get alternating lines of constructive and destructive interference. So on the antinodal lines, we see that the path differences have to be whole multiples of a wavelength. That's the condition for constructive interference. Now, what about the nodes that are in between? So let me erase this little guy here. What about on the nodes? What's the path difference there? Well, you're in between, right? So what's happening is, because a crest and a trough are a half a wavelength apart, if the path difference is a half of a wavelength, okay, then you're going to get destructive interference. And here on the next one, see, the path difference from the two sources is going to be 3/2 of a wavelength, so 1.5. Okay, so if you see what's happening here, in the middle the path difference is 0, then it's half a wavelength gives us destructive interference, the path difference. If it's a full wavelength, it'll go back to constructive interference again. If it's a full wavelength plus another half, that's 3 halves, that's destructive interference. 2 full wavelengths gives us constructive interference again. So this path difference on this line would have to be 2.5, which is 5 halves of a wavelength. Okay? And then finally this one over here, then we go to 3 wavelengths, 6 halves, right? Gives us constructive interference. And then this one would be if the path difference finally was 3 halves, which is 7 halves of a wavelength. Sorry, 3.5, okay, which is 7 halves of a wavelength. So I hope you get it. Like, what's happening is, as you radiate out from the middle, you're going to get alternating lines of constructive and destructive interference based on the path difference of waves coming from one source compared to the other. Like, they're following these yellow highlighted lines, okay, radiating out into the picture that you see. But on the nodes, okay, nodal lines, you get path difference, which is equal to Pn S1 minus Pn S2. And again, we put these absolute value signs because that depends on which side of the center you're on. But for the nodes, N, we don't start at 0 because like there's no 1 down the middle. So we start at 1. And so on. Okay. And for what we find is that the path difference for the nodes has to equal n minus 1/2 times a wavelength. So if n is 1, you get half of a wavelength. If n is 2, you get 1.5. If n is 3, you get 2.5, and so on. Okay, and this is a condition for destructive interference. So we call these dark lines, nodal lines. We'll just say it like this. These are AKA, I should have said this before, AKA minima, dark fringes for light. Okay. Okay, and those are areas or lines of destructive interference. Okay. All right, now I know this is getting long already, okay, but that's the first formula, that when the path difference is equal to, by path difference what we mean, okay, so if I'm going to erase this, if I'm a wave and I'm starting at S1 and I'm going to travel to the third nodal line, okay, so if you like, the first nodal line is n equals 1 right there, n equals 2 right there, n equals 3 on that one, and here we have a fourth one, n equals 4 right there, okay, and here n equals 1, n equals 2, n equals 3, okay, and n equals 4 on that last line of destructive interference. The blue lines, we number them that way. So you number them left and right of center, starting the one that's just right of center, we call it 1, or just left of center is the first one on either side. Okay, so if I'm going to go on the third nodal line, which is n equals 3, okay, and let's say I'm going to go to, I'll use a highlighter, let's say I'm going to go to this point right here. Well, in order to get there, I will have to travel that way from source 1. But if you're another wave starting at source 2, you're going to travel this way. Now you're way ahead of me because you're so much closer to it. So you're going to have passed me, and in fact, it's going to be a wave that is behind you that will meet me there. Okay. So if I'm a crest and I started at source 1, I will find that I'm always going to meet up with a trough from source 2 because the difference in the length of these two yellow lines, okay, is equal to anywhere along that line 2 halves of a wavelength, okay, or 2.5 wavelengths, right? And because the 0.5 is there, I'm always going to meet up with a trough. So a crest will always meet a trough at that point, okay? All right. The bottom line is, guys, you have to be able to use these formulas. So I took 30 minutes to explain these pictures to you. So I hope it's worth it, okay? And I hope you watch the whole video and try to understand it. I know it's a little, all these things they must be hard to watch, but anyway, I'm doing the best I can here. Okay, so what we're going to do now in the next series of images that you see here, and I'm just going to move these a little because they're kind of jammed up together. I never know exactly how much space my notes will take. Okay, so hopefully the mouse will start responding. Okay, so here, I'll move this down, and I'll move this guy as well. All right, so now, this will be my longest video of all time, I'm sure, and I knew it would be too. Okay, so here's the deal. By the way, all of this is in your textbook, so if you really don't want to listen to me, if you really want to read it on your own, maybe that's quicker for you, you be my guest. Okay, it's all there. All right, so now we're going to concentrate on the nodes for a moment. Okay. All right, so on the nodal lines, the dark fringes, or the shaded out areas there where you see like the destructive interference, what we're going to do is we're going to construct a little picture. So what we're doing now is we're taking the waves out of the picture, because these diagrams with all the waves in here get really messy really fast, right? So if you look at it, look at all those lines I've been drawing there. So imagine if you took all the waves out of the picture, they're still there, but I only drew the yellow lines, the highlighted lines from S1 and S2 out to a point. Well, that's what this picture down here represents, okay? So Pn is a point on a nodal line, okay? This line here, this full line segment here, is PNS2, you get it? And the whole line segment here all the way down, they cut it off at A, but don't do that, just the whole line segment all the way from here to here, that is PNS1. Obviously PNS1 is longer than PNS2. Now what they're doing is constructing an isosceles triangle, cutting it off at A. So this little guy here, I'm going to rainbow highlight it. That guy there is the difference in length between the two lines, right? That is your path difference. You get it? That's your path difference. That's cool. Kind of clarifies, hopefully clarifies it for you. Okay, now what they've done, what they're going to do in here is construct a little, they're going to zoom in. I say, all right, let's call that theta n. Okay, and d is a new variable that's introduced. D equals the distance, okay, S1, S2 distance, okay, the distance between the two sources. Now, this is an approximation, you're not gonna like this. They're gonna say this is approximately a 90-degree angle. Now, this is an approximation, okay? And it's a good approximation if the point on the nodal lines is really far away compared to the distance between the two sources. And for the laser experiment we'll do later, it's perfect. Works out perfectly. So it's only an approximation, but if we do this in class, you'll find it's a pretty good one. It works really well. And what you do is you go like this, sine theta n equals this, which is your path difference, right? Again, I'll highlight it. That's your path difference. So it's equal to path difference divided by d. Now, we know on the nodes that the path difference has to be an odd multiple of a wavelength. So therefore, we've just proven another formula, sine theta n write that again, sine theta n equals n minus 1/2. 1/2. Oh my goodness, what is wrong with me? Sorry guys. Times lambda over d, like that. I'm going to put this in a little box. That is a very useful formula. Okay. Now, there is another formula that comes up, and this one's actually super useful, where they do it like this. Let's say you construct this picture. So here's our two sources, all right? Here's our little, triangle that we just constructed at the bottom. There's theta n, okay? And then what they do is they construct what's called a perpendicular bisector down the middle, okay, or the right bisector, okay? And then you have your point on the node, and they call the distance from the center to the point on the node xn. Okay, remember these are nodes. The waves are in the picture above, okay? And what you're going to find, and you do the math here as another approximation, you're going to find that these two angles are equal, okay? Now, this is also a right angle triangle. So in this triangle, the sine of theta n would equal xn over L, okay? Where L is this distance from the right bisector, the midpoint of the right bisector right here, out to our node, okay, the point on the nodal line. So what we're going to say then, therefore, combining the two equations that we just did, is xn over L equals n minus 1/2 times lambda over d. Okay? So that's a lot. That's where we're going to end this today. So I know it's a 41-minute video. I'm sorry it's so long, but it's a long one. I need to explain the whole thing. I'm not sure doing it this way. It would probably take even longer if we did it live. Okay, so if we did a live video lesson, maybe this way you can rewind it and look at it at your own pace and everything else. But just to summarize here, okay, I'm going to summarize at the bottom. The really important thing is you know what each of these variables represents, and then you can do the homework questions. So the summary, okay, for 2-point source interference, okay, interference, well, I spelled interference, that's not right. Okay. For the antinodes. And by the way, we can do the same math with the nodes and the antinodes, so I'm just going to summarize it here. You get the path difference to any antinode has to be m lambda, pardon me, where m equals 0, 1, 2, 3, and so on. So m starts at 0. Also, you can get this, xm over L. Actually, I'll write it like this, sine of theta m would be m lambda over d, and xm over L would equal m lambda over d. Okay, that's for antinodes. Now for nodes, or nodal lines, it goes like this. The path difference equals n minus 1/2 times a wavelength, where n is equal to 1. No 0 this time. 2, 3, 4, and so on. Okay, and you get sine of theta n equals n minus 1/2 lambda over d, or xn over L, the last one, is n minus 1/2 times lambda over d. Okay, so that is the summary of all the equations that you need for 2-point source interference. Please remember you're always looking at this picture, like that's the picture that you're describing with this, okay? And we're going to show that the laser does exactly this thing. And what we're doing, okay, the goal of this is to give you tools so that when we look at the laser experiment, you can find the wavelength of the light, which is what Thomas Young did. He didn't use a laser, but it's what our goal is, okay, with 2-point source interference, is actually to do an experiment to measure the wavelength of a light wave, okay? So this summary sort of says it all. I know there's a lot in these notes. I know it's a really long video. Okay, 45 minutes now. But yeah, it shows you where all the equations come from, what all the variables mean. Okay, now for homework, I just want to show you where we are in the homework. Okay, so 2-point source interference. What we're at is here. 2-point source interference. Give it a try. Okay, and then we are gonna, everything else will go very quickly. Okay, so we're gonna go very quickly through the rest of it. Nothing takes as long as this. This has been our longest lesson of the year online. So I hope I didn't test your patience too much. And otherwise, have a good day, guys, and we'll talk to you soon.